Hey class, welcome back to Electromagnetics. Been going through the differential form of Maxwell's equations, but I want to stop for a minute and uh, look at this concept of curl and introduce Stokes Theorem, so that's what we'll do in this lecture. Thought for the day, Luke 16:10, I thought this was an appropriate verse. It says, "Whoever can be trusted with very little can also be trusted with much. And whoever is dishonest with very little will also be dishonest with very much." So this kind of echoes a little bit about what we'll be looking at today with curl and Stokes theorem, which Stokes theorem kind of says that, as we look at smaller instances of what's going on, that we can also evaluate on a larger scale and get the same answer. It's kind of an interchangeable theorem that we'll look at. So same way here, if we can be trusted with small things according to the word, then we should be able to be trusted with much larger things as well. Again, just to reiterate, we're still in part 3. We've done Faraday and Ampere's law, but we're taking a little bit of a break before we move on to Gauss, just to make sure we spend a little time on what the curl of a vector means and then how that relates to Stokes' theorem. So we want to take a little closer look here at this del operator as we use it to calculate the curl of a vector. Remember, if we have del crossed with a vector, that means that it can be restated as the curl of a vector. We want to try to understand exactly what this operator is telling us, especially when we get down to the point level. So with this, we'll also look at how this operator can be used to invoke Stokes' theorem and its application, which is a very useful theorem when dealing with electromagnetics and the mathematics involved with that. So to do this, we want to consider a simple case of Ampere's law in differential form without the displacement current density. So in other words, it's just del cross H is equal to J, or the curl of the magnetic field is equal to the current density vector. So we wish to now express this at a point using an infinitesimal area shrinking down to that point as follows. So we'll take this curl of H and we'll dot it with this vector area. So remember, that's the vector normal to the area as the magnitude of the size of the area and normal to it. And that should equal to the current density of that same area as we dot it with that. But the right side of this is simply the current crossing this this area, right? So then according to Ampere's law, this should be equal to, from the integral side, if we integrate around the contour that's enclosing this surface of the magnetic field along the vector distance of this contour, that those should be equal. That's what Ampere's law in integral form tells us. So that being the case, we could rewrite this equation up here with this substitution, right? And so we just replace the J dot the current density dotted with the area with this integral. And so this kind of is the jump start of our analysis here. So we can rewrite this again then. Remember, this is a vector, and so the del S, the magnitude of it, would just be the area of this surface, and then the AN is the vector normal to the surface, as we said a while ago. So again, that AN is normal, it's unit vector normal to this in all directions going around the surface. So we can now use this and divide both sides by this delta S. So we take this original equation at the top and we divide it by this delta S, and when we do, we get this resultant equation here. So we should be able to note here then that the maximum value of the right-hand side occurs when the left-hand vectors are parallel, right? So to restate that, the magnitude then of this vector, this curl of H, this would be the maximum that the right-hand side could be. Since the direction of the left-hand side is the direction of the current density, we can rewrite this again to say that the curl of H then is the maximum of this again in that direction normal to the surface area. So the above is only an approximation then, since it depends on the differential surface shrinking to a point. So we can improve this then by taking the limit. So we're going to take the limit as this differential area shrinks down to 0. And so now the result then is we have the curl of H defined, or the curl of the magnetic field defined in terms of the magnetic field at a point. This right here is considered to be the starting point for the formal introduction of the concept of curl. So the significant thing about this expression then as it relates to the curl is that as we shrink this differential surface, the limiting value to which the maximum circulation per unit area approaches the magnitude of the curl. So likewise, the limiting direction to which the normal vector to the surface approaches is the direction then of the curl. So in physical terms, what this tells us then is the curl gives us an indication as to the magnitude and direction of the maximum change in field intensity as we start to move away from the point. So this, in a sense, will give us the circulation per unit area, or the rate of rotation, or the tendency for the field to twist at a single point. So this allows us now, hopefully, to have a little bit of an understanding of what the field or fields are doing in the immediate area in relation to our point of interest. So a useful graphic to think about this then is we have this channel of water, and it has a certain flow, and you can see the profile of the flow here as we move across. At the walls, there's almost no water flowing. And then as we move towards the center, the maximum amount of flow is flowing in the middle. It's more rapidly flowing there. So if we were to take this little bob here, floating bob that has this paddle pinwheel thing on the bottom, if we were to drop it in at the center, then we would expect the little pinwheel thing to stay stationary as it went down the way, right? So this is velocity in terms of z, and it would just float down the way. Well, if we put it on either side, since the flow is greater on the right-hand side than it is on the left-hand side, our pinwheel bob would still go down the channel, but you can see since this flows more on this side than is this side, it will start to rotate in a counterclockwise position. Here we don't see any rotation because it's the same amount of flow on each side. Likewise, if we do it to the right, it'll start to turn in the clockwise rotation as it flows down the channel because there's more flow on the left side than in the right. And so this is the concept of curl. This is telling us that as we move away from our point, what's the tendency of the fields to turn, some charged particles or some other charged substance. So we can now use this to apply to illustrating and understand the physical interpretation of the curl of a vector field in relation to the behavior of electric and magnetic fields. So, for example, if we look at Faraday's law, the curl of the electric field is going to be equal to the partial of the magnetic flux with respect to time. So this tells us that at a point in an electromagnetic field at which this term, this time-varying magnetic field, is non-zero, that there will exist an electric field with non-zero circulation per unit area in the plane normal to this field. So that tells us as we have field lines going in this direction, we'll have an E field wanting to circle around it. Similarly, if we consider Ampere's law, the curl of the magnetic field equal to the current, both real and displaced, this tells us that at a point in an electromagnetic field at which the current is non-zero, there will exist a magnetic field with non-circulation per unit area, non-zero circulation per unit area, in the plane normal to the vector of this field. So again, as we have current flowing like along the edge of this paper, it's going to make a magnetic field rotating around that perpendicular to that. So now that we hopefully have a little better understanding of what the curl of a vector means or what it's telling us, we can use this relationship then to derive from this analysis to derive a useful tool in vector calculus known as Stokes Theorem that relates the closed line integral of a vector field to the surface integral of the curl of that vector field. So to do this, we want to consider some arbitrary surface. So we have this surface here, S, and it's bounded or defined by this closed contour C. So we have C as our contour, and the whole area inside of it is S. So we will then divide this surface into an infinite number of smaller surfaces, delta S. So this would be delta S1, delta S2, delta S3. They're still all totally enclosed by C. But then they've also had the smaller contour C1, which is related to delta S1, C2, which is related by delta S2, so on and so forth. So we can now apply the relationship derived in the curl expression earlier to the situation as follows. So we're going to say the sum of all of these curls of these smaller, infinitesimally small areas would be equal to the summation around each of the contours separately. So summing up just these curls dotted with these surface vectors, and then summing up, just each individual contour that defines those surface areas. Again, where this ANJ is the unit vector in the direction normal to the surfaces of S. So the left-hand side then approaches the surface integral delta cross H, or the curl of H, over S. And the right-hand side is simply the closed line integral of H over C. So then we could rewrite this then as the sum of the surface del cross H dot ds with the closed integral of the contour H dotted with dl. So we've got the curl of H summed over the surface is equal to H, or the magnetic field, dotted with the contour. This in itself is Stokes' theorem for vector fields, and so this is pretty handy. Many times we'll have integrals either in one form or the other, and the execution of that integral could be complicated. So if we know this theorem, sometimes we can substitute back over to the other side, which is a much simpler evaluation. So let's look at an example of this and how this works. We're going to take a certain problem and try to evaluate it both ways, using the left-hand side and the right-hand side of Stokes' theorem, and show that they do, in fact, agree. So here we're going to consider a vector A, which is just y in the x direction minus x in the y direction. And we're going to consider that in relation to the closed path here. So this closed path, we start at A, we go straight up the y-axis to B, then we go from B to C along this unit circle, and then from C we go back to A. So we first want to determine what the integral of A dotted with dl, so the integral of the A vector all the way around this closed contour. And we do this by evaluating the line integral along three segments. So we've got the segment here, and here, just breaking it up. So to do this, first we want to note that if we just take A dot dl, that's going to give us y dx minus x dy. Okay, so again, we're going in the dx direction on this axis, the y direction, and dy direction in this direction. So seems pretty simple that that's what that would give us. And so from this, we note that from a to b, that x is equal to 0 and dx is equal to 0. Therefore, the evaluation of this integral will give us 0 every time from a to b. Likewise, we note that from point C to point A, that's going along this path here, that y is equal to 0 and dy is equal to 0. So again, for integrating from C to A, this dot product, the integration of it, will give us 0. So we want to now continue with our analysis here. And so finally, we've got that final path from B to C. So remember, we have that defined by this unit circle, x squared plus y squared equals to 1. We can solve this for y, which gives us y equal to the square root of 1 minus x squared. Also, we note that 2x dx plus 2y dy is equal to 0 doing the limits of integration. And so solving for dy, we simply get negative x dx over y. Well, we have an expression for y in terms of x, so we substitute that in, and we get x over 1 minus x squared square root dx. So again, remember, this is the derivative of this guy. 2x dx plus 2y dy equals derivative of 1 is 0. And so these should be all we need to evaluate this. So now if we go back and look at a dot dl, we can substitute back in to this equation, and we get 1 minus x squared dx plus x squared over 1 minus x squared dx. Okay, and so when we do that, we can get a common denominator here, and so it'll be multiply this by 1 minus x squared square root over 1 minus x squared square root. Like, give us our base is the same, and this becomes 1 minus x squared, so the x squareds drop out, and so we're left with dx over 1 minus x squared square root. So now when we go to evaluate this integral from b to c, in terms of x, our x value just goes from 0 to 1. Here's our a dot dl term here. When we evaluate this, it's inverse sine of x from 1 to 0. We plug the values in, and we get pi over 2. So finally, evaluating this line integral, remember from a to b it's 0, from c to a it was also 0. The only non-zero part is from b to c. We just evaluated that on the last slide. It's pi over 2. So the total for this entire line integral is pi over 2. Now we want to test Stokes' theorem and evaluate this again using this format. Instead of worrying about the path around that space, we want to integrate across the area within that space. So for the plane surface S enclosed by C, we have that ds is just going to be minus dx times dy az. So that's just the area of our differential area of our space inside the contour. And from a previous example, we know that the curl of A at this point is going to be negative 2 az. Therefore, we can now evaluate this integral as follows. We've got the Stokes theorem, left-hand side of Stokes theorem. We've got to have a double integral because we're doing an area. So x is going to go from 0 to 1. Y, which is goes from 0 up to the point on that curve, the unit circle. And then we'll have 2 dx dy for our limits of integration. And so when we do that, this should be just the area enclosed by C, right? Well, we should know that the area enclosed by C is just the fourth of a unit circle, which should give us pi over 4, simplified things for us, multiplied by 2, and that gives us the final answer, pi over 2. So we've now tested Stokes' theorems and found that for this vector and the closed path, and the area inside the closed path, that both sides of this integral are equal to pi over 2. So again, it's two different ways to evaluate the same thing. And so you might run across in electromagnetics that you come down to an equation or an integral that looks like one side or the other. Sometimes it might help to do a transformation using Stokes Theorem to make it easier to evaluate.